In section 5.4 we did the fundamental theorem of calculus, and there when we took the antiderivatives or the definite integrals we stuck basically to the more basic trig functions and polynomials. Here in section 5.5 we're going to cover integration by substitution, and it's sort of reversing the chain rule. And in this section we're going to use pattern recognition to find indefinite integrals, use a change of variables to find an indefinite integral, use the general power rule for integration to find an indefinite integral, use a change of variables to evaluate a definite integral, and evaluate a definite integral involving even or odd functions. But first let's go back and revisit the chain rule very quickly. Here we are taking the derivative, d dx, the derivative with respect to x of x squared plus 3 quantity to the third. And when we derived this, the chain rule said we brought the 3 down front. So we had 3 times our inner function, x squared plus 3, and we dropped the power down 1 to squared. And then the chain rule said we had to tack on the derivative of the inner function. And here's our inner function. Its derivative is 2x. So now that we know the fundamental theorem of calculus and the relationship between deriving and integrating, it makes sense that the antiderivative of 3 times the quantity x squared plus 3, quantity squared times 2x, is equal to where we started. X squared plus 3, quantity to the third power. So we have to start looking for patterns and recognizing these patterns to see what's going on. So let me back up here a little bit. If I were to give you this and say find the antiderivative of this mess, the patterns we have to look for are inner functions and their derivatives. So here, usually if something's in parentheses, that might be your inner function. That's the best place to look. So I'm looking at this mess to the right of the integral sign, and I see an x squared plus 3 quantity squared. And I'm going to say, okay, well that might be my inner function. What is my inner function's derivative? Well, the inner function's derivative is 2x, and I have that inner function's derivative. So that's what I need to perform the antiderivative. And with our constant multiple rule, I could sort of bring this, well actually we'll leave that right there. When we integrate, we take our thing and then raise the power by 1. So this is my inner function that I've underlined here in red. My inner function, I am going to raise the power by 1 to 3, and I'm going to divide by the new power. And since I had a 3 out front there, that cancels out. So I'm back to quantity x squared plus 3, quantity to the third power. The inner function's derivative. Remember when we did the chain rule, we brought the 3 down front, the inner function stayed the same, the power went down 1. This was sorta, you could think about it as being created out of thin air via the chain rule. Now that we are going in reverse, this extra piece, this inner function's derivative, is sort of consumed in the process. We raised the power by 1 to 3. We divided by the new power 3, which canceled with the 3 we had in the front. The inner function's derivative is consumed in the process. Here it was created out of thin air. Here we consume it as we take this antiderivative. So pattern recognition. In this section you're going to study techniques for integrating composite functions. The discussion is split between 2 parts: pattern recognition and change of variables. Both techniques involve a U substitution. With pattern recognition, you perform the substitution mentally. And with the change of variables, we write the substitution steps. Now for right now, a lot of this calculus notation can get a little confusing with all the inner functions and outer functions and primes and whatnot. It might be a little confusing if we go over this right now and then dive into the examples. What I'd like to do is dive into the examples and maybe after the video come back and read through this on your own. It probably is going to make more sense after we do some of these problems. But here's our theorem 413, the antidifferentiation of a composite function. Let g be a function whose range is an interval I, and let f be a function that is continuous on I. If g is differentiable on its domain and f is an antiderivative of f on the interval I, then here is our integral, our antiderivative of the function of g of x and g prime of x. This is our inner function. This is our inner function's derivative. When we take the antiderivative, we get capital F of our g of x function. Again, the g prime, that's our inner function's derivative, is consumed in the process, so it disappears. And then we add our variable c, since it is not a definite integral. It's just the antiderivative. Later, when we talk about u substitutions, our g function is substituted with our u, and g prime of x dx is our du. So then we take the antiderivative of f of u du, it becomes capital F of u, and then plus c. The du was consumed in the antidifferentiation process. Note, the statement of Theorem 413 doesn't tell how to distinguish between your f of g of x and your g prime of x, your inner function and its derivative in your integrand. As you become more experienced at integration, your skill in doing this will increase. Of course, the key part is familiarity with derivatives. So the next two examples, 1 and 2, show how to apply Theorem 413 directly by recognizing the presence of our inner function and our inner function's derivative. Note that the composite function in the integrand has an outside function f and an inside function g. Moreover, the derivative g prime of x is present as a factor of the integrand. So again, here's our outside function f, here is our inner function g of x, and here is the derivative of the inner function g prime of x. When we take the antiderivative, we get capital F of the g of x function plus our arbitrary constant. So here in example 1, we're just working on recognizing this pattern. So when we look at this, again, a good rule of thumb is if you see something in parentheses raised to a power, it's a good bet that's your inner function. So our inner function is x squared plus 1. What is our inner function's derivative? Well, the derivative of x squared is 2x. The 1 derives away. So we will also need a 2x. And look, right there it is. So this is our inner function, and this is our inner function's derivative. So we can sort of just take the antiderivative of this part. So that is a quantity to the second power. The antiderivative is going to be the same quantity, x squared plus 1, raised to the new power of 3, and we could either divide that by 3 or put a 1/3 in front. 1/3 x squared plus 1 to the third power. And because this is not a definite integral, it's just an antiderivative, we got to add our arbitrary constant c. The good thing about these, if you want to check your work, we can just apply the chain rule here and see if we get back to where we started. So if I want to derive this, if I want to take the derivative with respect to x of what we just found here, this antiderivative, we would bring the 3 down front. 3 times 1/3 is 1. Here we have our quantity, our inner function, x squared plus 1, but now it's dropped down 1 power. And then we take the inner function's derivative. The inner function's derivative would be 2x. The arbitrary constant c would be derived away to nothing. Did we get back to where we started? Yes, we did. Let's see what's going on here in example 2. We have a trig function of a quantity, and that quantity is more than just x, so it's a good bet that this might be our inner function, 5x. So what is the derivative of 5x? Well, it's 5, and we have a 5 right there. So it looks like we're going to be good to go. So we need to ask ourselves, well, what is the antiderivative of cosine, or what do we derive to get cosine? Well, that's going to be the sine of the same 5x. And again, our 5 and dx are consumed in this antidifferentiation process. We have to tack on our arbitrary constant plus c. And again, let's check this to see if we are correct. So we're going to take the derivative with respect to x of sine of 5x plus some constant c. Well, the derivative of sine is cosine of the same 5x. And then the chain rule says we have to take our inner function's derivative. The derivative of 5x is 5, and here I'll put it at the front. And that exactly matches what we started with. So identify your inner function and make sure that inner function has a derivative present. We need that inner function's derivative. Here our inner function is g of x. The derivative is g prime of x. The integrands in those first two examples fit the pattern exactly. You only had to recognize the pattern. All the pieces were present. You can extend this technique considerably with the constant multiple rule. And remember, that just says we can have a constant in here inside the integral sign. We can bring it out front, k times that definite integral or indefinite integral. Many integrands contain the essential part, the variable, of the derivative g prime of x, but are missing just a constant multiple. In such cases, you can multiply and divide by the next necessary constant multiple, as shown in the next example, 3. When we start to look at this definite integral, we have a set of parentheses raised to a power. That's sort of a clue that that might be our inner function, x squared plus 1. What is the derivative of x squared plus 1? And I'm going to copy this problem here and leave myself a little space. Quantity squared dx. So our inner function might be x squared plus 1. Our derivative of the inner function would be 2x. We have the variable part. That's the important part. But we'd need a 2 here. We can't take the antiderivative without having the proper inner function's derivative. So we need this to be a 2x. But we can't just throw a 2 in there because that throws the whole problem out of whack. But we can balance it. If we put a 2 to the right of the integral to get our proper inner function's derivative, we can balance it outside with its reciprocal, 1/2. You can think about, like this. If I pull the constant multiple out again, the 2 times 1/2 would be 1. And 1 times anything doesn't change the problem. So here, our inner function's derivative was 2x. We had to tweak what we had with a 2. And we can't just do that without balancing it with a 1/2 out in front of our integral sign. So when we take this antiderivative, we're going to have 1/2. So here is our inner function that we're actually going to apply the antiderivative to. The 2x dx will be consumed in the process. So we take our quantity to the second power, and of course when we antiderive, we raise the power by 1, so we're going to raise that up to 1, or up to a 3, and we're going to divide by the new power, 3. And we have to add our arbitrary constant. And we can clean this up a little bit. This divided by 3 is the same thing as a 1/3 out front. And we can just multiply these fractions together. 1/2 times a third is a 1/6. And we have our quantity, x squared plus 1, quantity to the third. And you might think, should we distribute that 1/2 to the c also? Well, you could, but remember, c is just an arbitrary constant. It's some number, we don't know what it is. If we multiply that number by 1/2, it's still just an arbitrary constant, and we don't know what it is. So there is our antiderivative. Note, be sure you see that the constant multiple rule only applies to constants. You can't multiply and divide by a variable and then move a variable outside the integral sign. For instance, we have, this right here. Our inner function's derivative is 2x. There's not even an x there, let alone a 2. We have absolutely nothing. You cannot just put the 2x necessary there and, put its reciprocal out front, 1 over 2x. That only applies to constants. You cannot do it to variables. Because if this were a legitimate move, moving variable quantities outside the integral sign, you could just move the entire integrand out and simplify the whole process. But your result would be incorrect. Okay, on to change of variables. With a formal change of variables, you completely rewrite the integral in terms of u and du, or any other convenient variable. Although this procedure can involve more written steps than the pattern recognition illustrated in the first 3 examples, it's useful for more complicated integrands. The change of variable technique uses the Leibniz notation for a differential. That is, if u is our inner function, then du, the derivative, is g prime of x times dx. And the integral from our theorem 413 takes this form. Here was our integral of f of g of x times g prime of x dx. Well, this g prime of x dx just becomes your du, and this becomes f of u. Remember, our inner function is u. F of u du. When we take the antiderivative of that, we get capital F of u plus our constant. So let's see what's going on here in example 4. We have our our integral antiderivative of the square root of 2x minus 1. And we could rewrite that as 2x minus 1 to the half power. So our good bet for our inner function is going to be what's in the parentheses, 2x minus 1. So we are going to let u equal 2x minus 1. So du dx is going to equal 2. And then multiply both sides by dx. We get du equals 2 dx. Oop, and I forgot my dx here. So when we start to do the u substitution, oops, okay, we do have our inner function is 2x minus 1, but we need a 2 dx. And we have the dx, but we're missing the 2. So we are going to have to tweak this. I'll squeeze my 2 in right here in red. And because we put a 2 in to the right of the integral, we got to balance it with its reciprocal, or 1/2 out front. So let's see now. We have our 1/2 and the antiderivative. This is our inner function. That becomes u to the 1/2. And then 2 dx becomes our du. So 1/2, the antiderivative of u to the half du. Now this makes it a little easier. The 1/2 stays, constant multiple. We raise the power by 1, u to the 3/2, and we would divide that by 3/2, or multiply by the reciprocal, 2/3. And then we add our constant at the end. And because we just have a couple fractions here, we can see those reduce on the diagonal. We're left with 1/3 u to the 3/2 plus c. And now that we're done with taking the antiderivative, we can substitute our u back in. 1/3, and I'm going to leave this, or I'll put it back into radical notation. Our u was 2x minus 1. And that would be the square root of 2x minus 1 to the 3rd power plus c. Okay, in example 5, it looks a little more complicated here. We have an x outside, we have a radical. Again, I'm going to get that radical out of there and write it as a rational exponent. I'll leave a little space in here, x. And then we're going to have our 2x minus 1 to the half power dx. So I see a set of parentheses raised to a power. Good bet, this is my inner function. So we're going to let u equal 2x minus 1. So du equals 2 dx. So we're missing a 2. We have our dx, but we're missing a 2. So let me do this. Slide this over a little bit. I'll switch to a different color so it stands out. And here is my 2 dx. And because I put a 2 here, I got to balance it with a 1/2. So let's see what happens now. Something's a little different here. We have our 1/2 antiderivative. This is now going to be our u substitution, so that's going to be u to the 1/2, and then this becomes our du. But we have a leftover x. When we took our inner function's derivative, it was just 2 dx. We have something extra that we don't need. So we got to come up with something to do with this x. And if we go back to our u substitution, u equals 2x minus 1. Let's solve this for x, and we can plug that in for this x. So first, add 1 to both sides. U plus 1 equals 2x. Divide by 2. X equals u plus 1 over 2. So I'm going to replace this x with a u plus 1 over 2. And I don't like that, divided by 2. Remember, that's just a fraction. This divided by 2 I can drag out front as another 1/2. And since we already have a half out front, a half times a half is a 4th. And then we have our antiderivative of u plus 1 times u to the half. And let's distribute. U to the half times u to the 1st power is u to the 3/2. And then u to the half power times 1 is u to the half. and we have our du. So we're all set up to take our antiderivative. The quarter stays. And let's say we raise the power by 1. That's going to be u to the 5/2 divided by 5/2, or times 2/5, plus u to the 3/2 divided by 3/2, or multiplied by its reciprocal 2/3. Okay, and this next we'll do sort of a couple steps in one. Distribute this 1/4. We'll get 2/20, or 1/10. And let's plug our u back in. Our u is equal to 2x minus 1. And that's to the 5/2 power, plus distribute the 1/4 to the 2/3, and we'll get 2/12, or 1/6, u to the 3/2, and again our u is 2x minus 1 to the 3/2. Ooh, and I forgot my plus c. That's, oops. 3/2. Forgot my plus c there, and we'll put it right there. To complete the change of variables in example 5, you solved for x in terms of u. Sometimes that can be very difficult. Fortunately, it's not always necessary, as shown in the next example. So, ooh, this one looks tricky. We got our definite, or our antiderivative of sine squared of 3x times cos of 3x dx. So which is our inner function? We know sine's derivative is cosine, and cosine's derivative is negative sine. What gives it away for me is that squared right there. Because remember, there's an alternate way we can write that. We could write that as the sine of 3x quantity squared. You know, sine squared right here is the same thing. We can move that squared outside the parenthesis. So we have sine of 3x quantity squared, and then cos of 3x dx. So that, you know, that exponent is a red flag to me. This might be our inner function. So if we let u equal the sine of 3x, du is going to equal the cos of 3x times the derivative of the inner function 3 dx. So to put this in terms of u, you know, here's our inner function. Sine 3x is our inner function u, so this becomes u squared. Cos of 3x dx, cos of 3x dx, we're missing this 3. So I can tack a 3, you know, if I squeeze it in there, I could actually put it anywhere. If I put a 3 on the right of the integral sign, I got to balance it with a 1/3 out front. So here then we'll have our 1/3, and our 3 cos of 3x dx becomes du. So now where it's all in terms of u, this should be a simple integration. The 1/3 stays. And then we have raise the power by 1, u to the 3rd, divided by 3, or times its reciprocal 1/3. The du is consumed in the process, and we have our plus c. So we got a couple fractions here. 1/3 times 1/3 is 1/9. We can plug our u sub back in. So that used to be u to the 3rd, but now it's sine of 3x to the 3rd. Sine of 3x quantity to the 3rd plus c. And you know, just like we did in the original step, we moved that sine squared, we moved it up out here. We could put it back if we want. 1/9 sine to the 3rd of 3x plus c. And since that was a pretty tricky one, let's derive it and make sure we got the right answer. So, if I want to take this derivative, and I should write it back here, sine of 3x to the 3rd plus some constant. So we're going to do a little chain rule. The 3 comes down front, and we're going to have 3/9 of the same quantity, sine of 3x now to 1 power lower, and then we need to take the derivative of the inner function. Well, the derivative here, the derivative of sine is cosine of the same 3x. And then we have yet another inner function. The derivative of the inner function here is going to be another 3. So, just our constants, 3/9 times 3 over 1 becomes 9/9, or just 1, and then we have sine squared of 3x, times the cos of 3x, We got it. So the steps used for integration by substitution are summarized in the following guidelines. Choose a substitution, u, for your inner function, g of x. Usually it's best to choose the inner part of a composite function, such as a quantity raised to a power. Compute du, which is equal to g prime of x dx. Rewrite that integral in terms of the variable u. Find the resulting integral in terms of u. Replace u with g of x again to attain the antiderivative in terms of x. And if you want, check that answer by differentiating.